Welcome back to Business Calculus. This is the lesson for section 3.5, and just a reminder, 3.5 is the second part that is on homework and quiz number 9, and that homework and quiz is due Sunday, April the 5th at 11:59 p.m. Just as a kind of a reminder, all of these due dates and times are Central Standard Time, so we're still hanging on to our Starkville time, so if you're in a different time zone, please make sure you make note of that. All right, let's get started. Section 3.5 does have to do with what we call optimization. These application problems are primarily going to be rooted in business and economics types of problems, but you might see a few other ones also. So in this particular section, there are some kind of strategies for solving these word problems. Obviously, with any word problems, you want to make sure you read the problem carefully. Drawings are always nice. We try to provide you with some drawings, but obviously we can't draw everything. But usually drawing some type of picture is helpful in terms of helping you understand the material. Figure out what your variables are, what's going to be your constants, label your measurements on your drawings if you happen to have one. And then the big thing is going to be take that problem and translate it into an equation. A lot of times we talk about some type of quantity, we call it Q, and we're trying to maximize or minimize that quantity. When we're maximizing and minimizing, that means that we want to find the derivative. And so we're going to, sometimes we'll have more than one variable in a problem, so we're going to try to take one equation and write it in terms of another one so that we can end up with one function or one equation called Q, and it only has one variable in it. And then we'll be finding a derivative, setting it equal to 0. Same kind of things we've done in the first 3 sections of this chapter. So as I told my class the other day, if all else fails, once you get a function, find the derivative, set it equal to 0, and see what else happens. So at least it's a good jumping off point. So let's start with problem number 1. The problem says, of all the numbers that add to 70, find the pair that has the maximum product. And that is to maximize the what we call objective function Q, where Q is the product of two values. We also know that because it says all of the numbers must add to 70, then our two numbers x and y, the sum of those is 70. So sometimes you might just be given the first sentence of this problem, and then the second sentence is what you would actually come up with. So the objective function is what we're trying to maximize, because it says when we want to maximize the product, that's what tells us that our function Q is going to be x times y. When we also know that the numbers add to 70, that's when we have our two numbers x and y whose sum is 70. So obviously our two variables are x and y. We need to take this function Q and rewrite it so that we only have either x's or y's in it, not both. So my suggestion is the first step is to take this equation, x plus y is equal to 70, and solve this for y. So we're going to solve this equation for the variable y, and that's going to give us y is equal to 70 minus x. Now we can take this equation and substitute it into our objective function Q. So our second step here in our process is we start off with Q is equal to x times y, and so now Q is going to be equal to x times, and in place of y, we're going to drop in this new function here. So since y is equal to 70 minus x, in place of our y variable here, we're going to put in 70 minus x. And so this equation where we've solved for y is now coming back into this function. So now we've created this function Q, which is the product of x and 70 minus x. And when we multiply this out, we get 70x minus x squared. We now have a function which only involves the variable x. So then the third step in this process is to find the derivative of this, because we want to maximize this function and we want to find the value of x, which will maximize this function, and then we can use that value of x to find the value of y. So in order to find a maximum or minimum, we're going to find the derivative. Please note this is a quadratic function, so you probably have an idea possibly of what's going on, But if you're still going, yeah, no, I'm still trying to figure that part out, the process is you take your function, you find the derivative, and then the next step is we take that derivative and we set it equal to 0, and we're going to solve for x. And so this is going to give us negative 2x is equal to negative 70. There's several ways we can get to this point, and x is going to have a value of 35. Now, if we ended up with a value which is negative, that's probably not going to work very nicely for this problem. Since we're trying to maximize a product, we typically want it to be a positive unless they're both negative. Also, in this case, it's probably going to be something where we're going to get a nice positive number here, but we could have a negative number. It's not totally out of the realm here. Okay, so x is going to be this value. I would probably use the second derivative just to verify that this is indeed going to give me a maximum. So let's take the second derivative here, and the second derivative of this function is simply negative 2. This means that at x is equal to 35, the function is going to be concave. If you remember, a second derivative negative means that it's concave down, which then also means that at x is equal to 35, we will have a relative maximum. And so that's what we're trying to achieve here. So at x is equal to 35, we are going to get that maximum. So our maximum product is going to happen when x is equal to 35. So now the next step of this process is to actually go and find y. So we're going to find y by using y is equal to 70 minus x. And so y is going to be equal to 70 minus our x value of 35. And that means that y is also going to have a value of 35. Not terribly surprising in that a square usually results in a maximum product. So 35 and 35. So the two numbers are x is equal to 35. Y is equal to 35 and x is equal to 35. And those are going to be our two numbers which will maximize the product, whose sum is 70. All right, so let's move on to problem number 2. Again, we have a function we want to maximize. So we want to maximize the function called b, where b is the product of x times y squared, where x and y are both positive numbers. This is important, so that x plus y squared is equal to 1. So this is the function again that I want to maximize. So this is the function that I need to write so that it only has one variable in it. So my first step in this process is going to be to take the equation x plus y squared is equal to 1 and solve this. This time I'm not going to solve for y, but I'm going to solve for y squared. Why do you think that's the case? Well, the answer is because my function that I want to maximize has the term y squared in it. And since this equation also has a y squared, it just makes life a little bit nicer and easier. So now I have x plus y squared is equal to 1. And so if I solve this for y squared, I get y squared is equal to 1 minus x. And then I'm going to only have, again, one variable in here. So the next step in this process is to take my objective function b. So b is equal to x times y squared, and in place of y squared, I'm going to substitute this value or this expression that I found. So we'll just kind of highlight this here. Y squared is equal to 1 minus x, and so in place of y squared, I'm going to drop in the expression 1 minus x. So now my objective function b is equal to x minus x squared. Again, I have a very nice quadratic equation. So this is going to tell me again, this is nice. It is a negative x squared, which we know the graph of that opens down. Its vertex is going to be a maximum. So that just kind of confirms what we already know. The next step in this process, to go through this whole process, is to find the derivative of this, which is going to be 1 minus 2x. We're going to set that 1 minus 2x equal to 0. And this is going to give me negative 2x is equal to negative 1, and x is going to have a value of positive 1. It is positive, and that's what we need to make sure we have. It might not be a whole number. It doesn't say anything about being a whole number. It just simply says it needs to be positive. So again, I'm going to find that second derivative just to confirm that it does indeed produce for me a maximum. So the second derivative of this function is negative 2. This means that at x is equal to 1/2, which is our critical value from the first derivative, the function is going to be concave down. So it is concave down, which means that at x is equal to 1/2, we have that relative maximum again. So we are going to maximize the product. So maximize the function b, x is equal to y squared, when x has a value of 1/2. And now we just need to find the y value. So let's find y. And so we're going to use the fact that y squared is equal to 1 minus x, or 1 minus 1/2. So y squared is equal to 1 minus 1/2, which is 1/2. And now I need to take the square root of both sides. So if I take the square root, if you recall, the square root is going to be a plus or minus. So we have plus or minus the square root of 1/2. Now remember up here, though, it said y needed to be a positive value. So we're only going to use y is equal to the positive square root of 1/2. The square root of 1/2 can also be written as, we'll kind of clean this up just a little bit. This is the same thing. The square root of 1 is just 1, so 1 over the square root of 2. If the problem asks you to rationalize the denominator, you can also write this as the square root of 2 over 2 by multiplying numerator and denominator by the square root of 2. So in answer to our question, x is going to be, or this function is going to be maximized when x is equal to 1/2 and y is equal to the square root of 2 over 2. And those are our two values for x and y. Right? Now, it's probably going to ask you to leave it in this form. If it does ask for a decimal, you can plug that into your calculator and get a lovely decimal. All right, let's look at this problem. I'm going to move this up just a little bit. So problem number 3 says now we want to minimize our objective function e, where our objective function is given to us as x squared plus 2y squared, and we are also told that x plus y is equal to 3. Now there are no restrictions on x or y here, but we are going to be minimizing this function. Minimizing or maximizing, we still want to take our function, write it in terms of one of our two variables, not both of them, and then find that derivative. So we typically like to work with our x's. I don't know, it just seems more comfortable for us. So we're still going to start with this equation right here. So we'll start by taking x plus y equals to 3 and solving this for y. So we're kind of gotten into a habit here. So we'll subtract x from both sides. So I have y is equal to 3 minus x. So the next step in this process is to take my objective function e, which is equal to x squared plus 2y squared, and I'm going to substitute this y value in place of that y term here. So I have x squared plus 2 times, now y has to be squared, and in this case I don't know what y squared is, I just know what y is, so I know that y is equal to 3 minus x, so in place of y here I'm going to put in 3 minus x, and so this quantity is going to be squared. Now in order to find the derivative, you can use your your power rule and then your chain rule to find this derivative. That's probably what I would do. So the next step in this process, in order to minimize or maximize either one, is we need to find the derivative. So the derivative of x squared is just 2x. The derivative of 2 times 3 minus x quantity squared is going to be 2 times 2, which is going to be 4. We're using this chain rule. 3 minus x now to the first power, and then times the derivative of what's inside, which is negative 1. Be very careful here because that negative 1 is kind of sneaky. So if I clean up this derivative, I have 2x plus, And in this case, actually, we're going to go ahead and change this to a negative because I have a negative times here. So I'm going to have negative 12, and then I'm going to have plus 4x. So I'm distributing, I'm kind of collecting these two together first, and then I'm distributing that through here. And so when I clean this up one last time, I'm going to get that my derivative is 6x minus 12. So now I need to find that critical value, which will hopefully minimize this function. And so my critical value is going to be found by taking 6x minus 12, setting this equal to 0. So 6x is equal to 12, and x is going to have a value of 2. So again, I'm going to find that second derivative just to confirm that this is indeed going to give me a minimum. So the second derivative of this function is going to be just 6. So that means that at x is equal to 2, the function is concave. If the second derivative is positive, that means it's concave up. And if it's concave up at our critical value, then at x is equal to 2, we have a relative minimum. And that's what we're wanting to get. So to minimize this objective function, minimize my objective function e, which is equal to x squared plus 2y squared. We minimize this at x is equal to 2, and now we need to find the y value. So in order to find the y value here, we're going to use our equation. We're going to use y is equal to 3 minus x. And so y will be equal to 3 minus our x value of 2. And so we discover that to minimize this objective function, we have at y is equal to 1 and at x is equal to 2. Those two indeed do give me 3, and they will give me the minimum value for this function. I'm not asked to find that minimum value. I'm just trying to find those x and y values. If I needed to find, so if you need the minimum value, so the minimum of this expression e, this function e, then we would use e is equal to, and we would go back here and we would say 2 squared plus 2 times 1 squared, and this would be 4 plus, remember the 1's the only thing that's squared, 2. And so the actual minimum value of this objective function is 6. So when x plus y is equal to 3. So this is just an additional piece of information, but this would be the minimum value of my objective function e. Okay? So sometimes it asks us to take it one step further, so just in case. All right. So this is a little bit more of an application problem. So we have a very nice picture over here, so we'll talk about this. An open air waste management system is designing a rectangular construction dumpster. It will be twice as long as it is wide, and it must hold 12 cubic yards of debris. Find the dimensions of the dumpster that will maximize its surface area. So what I'm going to do here is I'm going to let this distance up and down, it's called question mark here, but we're going to call this H, and we're going to call this length here, we're going to call this Y. So I'm going to label these. So I have an X, a Y, and an H. So there's a couple of things that we need to talk about here, and the first thing is it wants to hold 12 cubic yards. Well, cubic yards should kind of remind you of a measurement in geometry, which is the volume. And so that's really what we need to start by talking about. So our objective function here, and this is one of these that you will see a problem similar to this, is volume. And volume is equal to, when we have a container like this, volume is equal to the length times the width times the height, so x times y times h. So the product of the three sides, or the three measurements in our container. This is a rectangular prism, and just in case you don't remember, that's how we find volume. Now, we do know what volume is equal to in this case, so we just need to find these values that are going to to help us out here. So we're going to use all of this information. The other thing is, actually, I lied to you. This is not my objective function. My objective function is going to use this. So we're going to use volume here. So I apologize for that. I wasn't paying attention to the question, which is probably very useful. We look for the word minimize when we're trying to figure out what the objective function is. And since it tells us to minimize the surface area, so let me erase this. It will disappear now from your screen. And so we're going to use that volume is equal to x times y times h, and we are going to use this 12 yards squared. But our objective function, because once again, please listen to this, our objective function is based on what we are being asked to minimize or maximize, is surface area. So now surface area for a prism like this is going to be the area of the 1, 2, 3, 4, and then the bottom is 5 surfaces. There is no top on this container, so and the problems that you'll see on your quiz, on your test, on your homework will be very similar to this. So please keep in mind we're going to start with the ends. So this side down here and then this end here, the area here, we're going to have 2 of these that are x times h. So 2 ends. Then I have 2 sides. I have this side here that says open air waste with this phone number, and then the side directly across from it. It's going to have a dimension of h times y. So I have 2 of those. So 2 height times y. And then finally we have the bottom of the container. So the bottom of the container has the dimensions of y times x. So only one of these. So kind of keep in mind here, this is the bottom of the container. This is the 2 ends of the container. And this is the 2, what I call kind of sides of the container. And that's what surface area is, and that's going to be our objective function, and that's what we're going to be working with. So anytime we've worked these problems before, we had to take the information we knew and we had to solve it for something. So we know a couple of other pieces of information here. This is kind of an involved process, but we can do this. We know that the dumpster will be twice as long as it is wide. So here is our width and here is our length. So from this information, twice as long as it is wide, I can write the equation that y is equal to 2x. So I'm going to take this information, I'm going to take the fact that volume is 12 yards cubed, and I'm going to put all of this together in an equation that I can solve for x. Okay, so or actually I'm going to solve for h, so I can plug this in. So here's what we're going to start with. We're going to start with volume of 12 is equal to x times, instead of y, we're going to have 2x and then h. So I know that volume is equal to x times 2x times h. So 12 is going to be equal to 2x squared times h, and then I can solve this equation for h. The height is going to be equal to 12 divided by 2x squared, or we can say that the height is equal to 6 over x squared. Okay? Now we're going to put that into our objective function. Because I know I'm going to be finding the derivative, you could also rewrite this as 6 times x to the negative 2, but for right now I'm going to see if I can get away without doing that. If need be, I'll come back and do this. So let's go back to this objective function. So we're going to take, once again, surface area is what we want to find the derivative of. I have 2x. In place of h, I'm going to substitute this expression that I have, which is 6 over x squared. And then I have plus 2 times, and in place of h again, I'm going to have 6 over x squared. And in place of y, I'm going to have 2x. Notice what I'm going to end up with is an equation, a function here for surface area that only involves the variable x. And so in place of y here where I have xy, I'm going to replace y with 2x. So now I am going to clean this up a little bit, and so now again my surface area only involves the variable x. When I clean this up, I have 12x over x squared. We will simplify that also. I'm just taking little steps here. 2 times 2 times 6 is going to give me 24. So I have 24x over x squared. And then finally, I have 2x squared. Cleaning this up as much as possible before I try to find the derivative will just make your life easier. This is 12 over x plus 24 over x. I can collect those together. Some of you may be 5 steps ahead of me. That's perfectly fine. This now is 36 over x. Once again, I am taking several little steps in here. If you can skip some of those, that is perfectly fine. So before we do anything, my surface area, I'm going to write this function as 36x to the negative first power, just rewriting this, plus 2x squared. This is my surface area function. This is my objective function. This is what I want to minimize. This is what I need to find the derivative of. So let's go to the next step in this process. So we're going to find the derivative of surface area. So the derivative of this function is going to be negative 36 x to the negative 2 plus 4x. This is what I need to set equal to 0 to find the critical values. I am going to make you very happy in just a minute and tell you you can skip a step, but for right now, we need to take negative 36 x to the negative 2 plus 4x and set this equal to 0. Now when I do this, I'm probably going to go ahead and rewrite this as I do this. So I'm going to have negative 36 over x squared, and I will subtract negative 4x, or subtract 4x from both sides. I'm going to multiply both sides by x squared, gives me negative 36 is equal to negative 4x cubed. And then I'm going to divide both sides by negative 4. So this is going to give me 9 is equal to x cubed, and x cubed is going to be equal to the cubed root of 9. Now, I know that is not an incredibly lovely number, but it is okay and we can work with it. Now, note that it should not say x cubed, that should say x is equal to the cubed root. Sorry about that. I think I said it, I just didn't write it. So somebody was probably trying to correct me. Now, what I'm going to tell you to make you happy is I promise that this will minimize the surface area. You can find the second derivative, you can use the first derivative test, but I'm going to tell you, you can skip that step now. So there may be some other people who tell you how to do it, but I'm just going to tell you, you can skip this step. This is going to minimize your surface area. You have done enough. So at this point, we'll just breathe. Okay? If you don't believe me, find the second derivative, it will minimize it, okay? So now I know what x is, and now I just basically need to substitute back in to find my y and my h, okay? So at this point, I want to find the value of y, and so I'm going to use y is equal to 2 times x, so 2 times this cubed root of 9. And so y is going to have a value of just 2 times the cubed root of 9. We'll come back and get some decimal values for these in a minute, just in case MyLabs Plus would like you to find the decimal values. And then finally, we have one more to find, and we want to, because it does say find the dimensions, so we want to find h. And so h, if you recall, is 6 over, and this is going to be squared, and so we have the cubed root of 9, and we're going to square this. All right, so let's go ahead, and I'm going to see if I have the Dream Calculator on my computer, and I probably do not. I do not. So sorry about that. We will drop that off. I'm going to pause for a second and plug some of these things into the calculator. You do the same thing, and we'll come back with some answers. See, you didn't even know I was gone, and through the magic of calculators, X is going to have a value of 2.08 yards, Y will have a value of 4.16 yards, and H has a value of 1.39 yards. Make sure you can plug those into your calculator. If you take X times Y times H, you get 11.9999, which is close enough to 12 cubic yards. And so that's going to be my final answer. Like I said, a little bit long of a problem, but I promise you if you follow this step by step, you will be able to do the problems that you see. Okay? All right, so we're going to remind you of a couple of formulas here. I'll scroll up so you can see them in just a minute. Some of these you've already seen before. Actually, all of these you should have already seen. So that's why it says important formulas to remember. Remember that cost, C of X, is a total cost function. If we're talking about maximizing or minimizing probably the average cost, it's C bar, and we use C bar to represent that average cost function, and that's going to be our cost divided by X. So just that's actually down here. Revenue is total revenue, R of X. P of X is total profit. Little p of X is our price function, also sometimes known as the demand function. So these are just some reminders. If we have little p of X, to create revenue, we do X times little p of X, or this is actually also known as the number of units. And we saw a problem similar to this that didn't have P's and X's in it. So it's the number of units times the price per unit. We saw that in a previous section. Some of you didn't like this. The number of units was Y, and X was a function of Y, and X was the price. So always remember revenue is number of units times price per unit. Profit is revenue minus cost if we're not given the profit function, and our average cost function, if we're not given that, is our total cost function divided by the variable X. So just reminders of some very important formulas if you don't have these written down at any other place. Okay. All right, so problem number 5 here says find the maximum profit. So again, because it says maximum profit, then our objective function is our profit function. That means since I'm given the revenue and the cost function, the very first thing I have to do is I have to find the profit function. Then I'll find the derivative and so on and so forth. It says find the maximum profit and the number of units that must be produced and sold in order to achieve that maximum profit. So we're also going to be looking for the value of X, and then we're actually going to be looking for the value of the profit. But before we can do anything else, the very first thing that we have to do is we have to find that profit function, remembering that profit is indeed our revenue function minus our cost function. And so our profit function for this problem is going to be 50x minus 5/10 x squared minus, I'm going to tell you, be very careful making sure that you do put this in parentheses, or just making sure that you distribute as you work the problem. So capital P of X is 50x minus 5/10 x squared minus 4x minus 10. That will make a difference. So this is going to be 46x minus 1/2 or 5/10 x squared minus 10. And so this is my profit function. I'm going to come back and use this in a little bit to actually find the maximum profit. But for the next thing we need to do is we're going to find the derivative of this profit function. So as I get ready to find the derivative, so it's going to be 46 minus, keep in mind that this is the same thing as 1/2. So however you do it, whether it's as a decimal or a fraction, 2 times 1/2 is just going to be 1. And so I have 46 minus x. All right. So now I want to take 46 minus x, and I'm going to set it equal to 0. This is going to give me negative x is equal to negative 46, or positive x is equal to positive 46. Typically in these profit, revenue, and cost functions, x is going to be a positive number because it's kind of not usually a good business practice to try to sell negative numbers of units, and people don't typically buy negative numbers of units. So most of these values are going to be positive. Just to confirm that this does indeed give me that maximum that I want. So the second derivative of this function is -1, and that means that it is concave down, and so we're just kind of confirming that second derivative case, which means that at x is equal to 46, we will get that maximum that we're looking for. So it does turn out it's actually an absolute maximum, but you can call it either one. That's not the point here. So we know that in order to the number of units that must be sold to maximize the profit, so we say up here to maximize the profit, 46 units must be produced and sold. Okay. Now, the maximum profit, however, so now we need to, so the maximum profit, so be very careful on these, maximum profit is going to be found by taking our value of 46 and substituting it in for x in our profit function. So 46 times 46 minus 1/2 times 46 squared minus 10 is going to be 1048. All right, so 1048 is our maximum profit. So this is the maximum profit, and it is realized when 46 units are sold. Okay, all right. Same song, second verse, find maximum profit and the number of units that must be produced and sold in order to achieve that profit. So a little bit different functions here, but we're going to go through this same process again. Step 1 is we need to find the profit function. That's what we're trying to maximize, so we actually need to find that profit function. So profit function again is the revenue function minus the cost function. So our profit function is going to be 2x minus, being careful here, I would just put this in parentheses. Too many mistakes are made by forgetting to distribute your negative sign. So that parentheses kind of keeps you out of trouble at least a little bit. So 2x minus 100th x squared minus 6/10 x minus 30. And so our profit function is going to be 2 minus 6/10 is going to be 1.4, or 1 4/10 x minus 100th x squared minus 30. And so now the next step in this process is to find the derivative of this function. So p prime of x is going to be 1.4 minus 200th x. Okay, and so then the next part is we're going to take this derivative and set it equal to 0. And so notice that as I solve this for x, and a lot of you guys will do this, is you're going to have these two negatives. And if you lose one of those two negatives, then what happens is you end up with x to be a negative value. And since we know that x can't be a negative value, that would kind of hopefully keep you out of trouble. So just be very careful there. So if I divide both sides by negative 0.02, I get that x is equal to 70. So again, just to confirm that this is indeed going to give me that maximum that I want. So I'm going to find that second derivative of this function. The second derivative of this function is negative 200ths, and so again this is concave down, and since it is concave down, then that means that at x is equal to 70 we will get a maximum. All right, and so to maximize the profit, then we need to produce and sell 70 units. Okay, and then the maximum profit is going to be what we get when we find P of 70. So plugging it into your calculator, this is when I wish I could say, okay, somebody help me out here and plug this into the calculator, but we will do that. And you may be thinking you've done this incorrectly, but it turns out to be 19. Now, once again, these are kind of contrived numbers because, $19, but it could be $19,000, it could be 19 million, we could be talking in whatever kind of units we happen to have. So, but 19 is the maximum profit, and that is obtained when 70 units are produced and sold. Okay? All right, we have one more problem, but it has several parts to it, so bear with me, we're getting close. Riverside Appliances is marketing a new convection oven. It determines that in order to sell X ovens, the price per oven must be given by, and it's given us a price function, so P of X is equal to 280 minus 4/10 times X. It also determines that the total cost of producing X ovens is given by this cost function. So the first thing it asks us to do in this problem is to find the total revenue. So this is simply another way to say find the total revenue function. Well, if you recall from a previous slide, revenue is equal to X times P of X, since we're given a price function and we're talking about selling X ovens. So our revenue function then, and this is all this problem wants me to do, is X times 280 minus 4/10 X. Now you can also, go ahead and multiply this out if you'd like to. I probably would. This is 280X minus 4/10 X squared. We're going to need to find the derivative eventually, so right now I would probably, like I said, I would probably do that just because it makes it a little bit easier to find the derivative later on, but you certainly don't have to. So, but we are going to be using this 280X minus 0.4x squared, or you can use the product rule to find that derivative in a minute. Okay, so the next thing we want to do is to find the total profit function. So our total profit function, remember, is revenue minus cost, and since we've now found our revenue function, then we can find our profit function. So profit is going to be 280x, and that's why I said I would probably go ahead and multiply it out. It's just a little bit nicer. Minus, and then our cost function, which is going to be 5,000 plus 6/10 X squared, and I put that in parentheses, so hopefully you are putting it in parentheses, keeps you from making careless mistakes. This is going to be minus 5,000 and then minus 6/10 X squared. So yeah, we did kind of make a little bit nicer numbers here, so sorry, some of your homework may not be quite such nice numbers, but you've got a calculator and lots of time. So all right, so now as I collect together like terms here, I have 280x because there's nothing to collect together. Negative 4/10 and negative 6/10 is negative 1, so I have negative x squared and then minus 5,000. Okay, and so giving you a second to make sure you've got that function, making sure that you've found all of the pieces, but this is my profit function, so we're going to use it on the next slide. All right, so we have our revenue function, we have our profit function. Let's see what else we can do with this. So the next part says how many convection ovens must be produced and sold in order to maximize the profit. So in order to maximize the profit, we need to find the derivative of the profit. And so let's recall that our profit function is 280x minus x squared minus 5,000. Those of you who know my memory is terrible, I cheated, I wrote it down somewhere else. All right, so now we want to find the derivative of this. And so the derivative is going to be 280 minus 2x. In order to find the number of units, the number of ovens that we need to maximize, we need to now find that critical value. And so we're going to take this derivative and set it equal to 0. And so I'm going to add 2x to both sides just so I don't have to deal with that negative. Doesn't matter, we're going to get the same result. And when I divide both sides by 2, I'm going to get 140. Now, just to make sure, I'd just like to remind you that the second derivative of this function is negative 2, which does mean that at x is equal to 140, we will get that maximum because it is concave down and it's going to give us that maximum. Okay, so we can answer this question by saying that we must produce and sell 140 ovens will maximize the profit. All right. So then the next part is, what is the maximum profit? Well, again, we're going to go back to our profit function and we're going to be plugging in 140. So the maximum profit will be found by plugging 140 in for this profit function. So we have 280 times 140 minus 140 squared, be careful there, minus 5,000. And as I put this into my calculator that you can't see, I'm going to get a very nice number of 14600, or $14,600 is the maximum profit, and that is obtained when 140 ovens are produced and sold. Now, here's the last question, and I need you to be really careful. This says, what price per oven will maximize the profit? So this we are going to go back because I really want to highlight this to you. Here is the function that we are now looking at and talking about. This is, and that yellow does not show up, this is the price function. And so this is the function that I'm going to need to use to find the answer to my last question. So let's go back to the last slide here. And so change this back. So price function, little p of x, is 280 minus 4/10 times x. And so this is where little p of x, I'm going to plug in the number of ovens, so 140 into this. So I have 280 minus 0.4 times 140, and I think I need to scroll this down just a little bit so that we can see this. And so we're going to have 280 minus 4 times 140, and we're going to get a price of $224. So in order to maximize the profit, so we can write a sentence, to maximize the profit, we must sell 140 ovens at $224 each, and then we will obtain a maximum profit of $14,600. So very application-oriented problem here. So I hope you have enjoyed the optimization section of business calculus. Have a great rest of your day. Bye-bye.